Amazing wing. And I was watching that plane go over the skyline, and I remember thinking, one airplane, hundreds of buildings, I bet this is a more stable business. And so one thing we might be selling is stability, you know? There's a technical fascination there, there's a need for it, there's an industry here, we just gotta figure out how to bring all that stuff together. All those machines are complex and interactive, and all that stuff is interactive. Like I do a whole ditty with that in some classes. And what really is important is the control systems, what's managing all that. So if you can master the control system and understand how to optimize the control system, man, you're on the road to delivering that savings from the fan all the way to the stack on the plant, and that's important, okay? One thing to remember though, when you're doing all this data stuff, is what you see may not be what's going on out there until you know the system and trust it. Like there's all sorts of things that can happen between here and here, like A to D conversions, accuracy, COV limits, all that kind of stuff. And then like bifocals, like you see a 3 and think it's an 8 and you react to the 8, and you know, and then there's hysteresis in the linkage. So what, you know, the advantage of the olden day way with the clipboard and thermometer is you walked up and you stuck it in and you said, that's the temperature. There's a lot between us. And so every once in a while, it doesn't hurt to go up with your thermometer and stick it in the duct, right? So another thing that happens, aliasing. You know, it could be, you know, if we knew the sensors, they were perfectly calibrated. It could be that, you know, all you really know when you're logging data on a 5-minute trend is what happened where those yellow dots are. These little pretty purple and blue lines, that's a regression Excel did, or whatever software. That's sort of saying, well, I know this and I know that, so I bet you it looks like this. Well, that could be true, but it also could be that, totally aliased, okay? And then this is another example of that, but how do you figure that out? Nyquist theorem. It's an amazingly complex derivation for a very simple principle. Basically, you need to sample a process at twice the frequency of the fastest disturbance in the process. So for me, what that means is most HVAC systems, before I know them, I'll run trends at least once a minute sampling rate. And you'll catch a lot of stuff that way. But what you won't catch, for instance, is a boiler short cycling, or the pump down cycle in a refrigeration system. So like a boiler, I might watch it fire and say, oh, the pre-purge cycle is 5 seconds, so I need to sample every 2 or 3 seconds if I want to see this. And that's how I'll deploy initially. And I get a lot of data and use up the logger fast, but I'll find a problem. Then I can back it off. But my point in bringing this up is we're talking a lot about data here. You've got to remember what you see may or may not be what's going on in it. And that's an important thing. Because you don't want to create like a house of cards, right? You don't want to represent a building as being really, really efficient, only to discover that you were reading the data wrong. It's a disaster. So just an important aspect, I think. Okay. So this is just a little Nyquist example if you're interested. I actually have a blog post with that on it too. So here's where, you know, what I really wanted to do is talk about leverage and technology to teach technology. And so what I'm going to suggest, like you've been listening to me yak here for an hour, why don't we take like a 5-minute break and then come back and I'll get a model up and we'll start working with the models a little bit. And I'm going to put all this stuff up on the website. If you want to pull it back, it'll be there. But yeah, take a 5-minute break, come back, and we'll start playing with the model. Settle in around the set point. That's unacceptable, okay? So having said that, here's what David was talking about and why it matters. Lags, what lags are basically is if you consider this heat exchanger, right? And if we say, well, let's look at what happens as information passes through that system. Basically, the controller has to react to the change, right? Now, in the olden days with the mechanical controller, there was a physical observable time for the levers and diaphragms to move. Now it's electronic, so that's pretty fast. If it's a pneumatic system, an air volume has to move through the pipe to fill the chamber that represents the actuator. The pressure behind the air, the size of the pipe, and the size of the chamber that have to be filled are going to introduce some sort of lag. There's going to be some finite amount of time that it's going to take to move the air to get the actuator to move, right? The actuator has to move through any play that exists in the linkage system, the hysteresis. The valve plug needs to move after the hysteresis is taken out. The steam has to accelerate into the heat exchanger, and then the saturation pressure of the steam has to equalize with the water and everything like that before the heat transfers. There's time associated with all those things. And then the warm water needs to move to the sensor location. And then the warm water has to warm up the well, which then warms up the sensing element before the controller can see that. Now, and here's a real, like I do a lot of, I bring stuff to classes. Deb pointed out that I've done that forever, but it really seems to help people connect. And so what I'm going to do is pass around something here. I'll tell you what to do with it in a minute. Or I'll maybe stand here. So these little sensors, little brown wires or the silver thing, they're all type K thermocouples, same accuracy class. They're identical thermocouples from an accuracy class standpoint. But if you look close at them, they really aren't identical. Like this one's in a sheath. This one is that little sintered bead, but that bead is bigger than this bead. So what does the size of the bead and the sheath mean? What about that? How's that going to impact my ability to measure things? Lag. It's a thermal lag. So you can do a little experiment when I pass these around. Just blow on it and watch how fast the little bead reacts compared to how fast the sheath reacts. This just plugs in. You just have to watch polarity. There's a plus. If you look close, there's a plus on the thermocouple. There's a plus on here. Just get the pluses lined up. I'll turn it on here and set it degrees Fahrenheit. And so you can, if you want, you're under no obligation to do this, but do a science experiment. And you didn't think this would be fun when you came today, right? How much fun are we having now, right? Okay, so that everybody got the concept of a lag, right? So here's the fascinating part about it. Okay, now this is the output from David's tool. Okay, above this on the screen, there's basically the PID equation, and you can adjust all the constants, and then there's an output equation that lets you put in like a couple first order or second order responses and lags and stuff like that. So I've actually used his tool to troubleshoot. When I was trying to figure out why a loop was giving me a hard time tuning, I'd guess at some of the parameters and see if I could isolate the problem just by playing with his model versus playing with the building, okay? But it's also a really great way to learn PID. And his book's set up with exercises, and in the software there's a little drop down and you pick exercise 1 and it sets it up for you. So it's very, very, very well thought out. But here's what's really interesting in a nerdy sort of way. This red line here, that's basically T0 is when the process is upset, okay? So you upset a process, and if the process was an open loop first order response, in other words, there's no control. You just turn the knob, the valve opens to a different position, the steam flow changes, the saturation pressure and the heat exchanger changes, and you stabilize at a new condition, okay? No control at all. That's what the red line looks like. The blue line is a process that has a little bit of control, a little bit of proportional control that's really loosely tuned, but there is some control, okay? The gray line is a PI process, or actually, yeah, I think it's PI, with virtually perfect tuning, okay? So that's a perfectly tuned process. The back line is a process that's almost over-tuned. It's on the verge of going unstable, okay? So basically from red to black, you're going from no control to too much control. Does everybody follow that? Okay. A couple interesting things. The time span between when you trigger the change and when the change is actually observable in the process, that's the combination of all those lags. It's called the apparent dead time. And actually, one way, the open loop tuning technique is you put the loop in manual, get it as stable as you can get it, introduce a step change, and watch for that apparent dead time, because you can calculate the tuning parameters off of that, okay? That's very useful, but to be honest, here's what's even more useful in my estimation. If you look at the natural period of that loop, the apparent dead time is about 4 times the natural period. If you do the math, it'll come out between 2 and 4 times the natural period. And David does the math in a sidebar. But you can also do a little thought experiment. If you just go through that heat exchanger process and pretend you're the controller, you make a change, and until that apparent dead time happens, you're not going to know what happened to react to it, right? So you get to at least 1 or 2 apparent dead times just by a little intellectual exercise, okay? Here's what's really cool about this. Basically, up until you hit about the second apparent dead time, all those processes' reactions are identical. An overtune process, a no control process, in the first half of the natural period, the response is identical. So what that means is, if you're tuning a loop and you're breaking something in less than twice the apparent dead time, you aren't going to fix it with tuning the loop. You got a lag problem, okay? You got to get rid of a lag. That's really hard. I've taken wells out to get rid of a lag because that's something I can control, right? I can't control the length of my duct, but I can. So that's very insightful. If you're banging your head against the wall trying to get a loop to tune and you keep hitting the safeties and stuff, you might want to do this open loop test and see what the apparent dead time is. Now, a lot of buildings, the building actually does the open loop test for you every morning on every control loop. You just aren't logging fast enough to see it probably, because this is probably going to be less than a minute on a lot of our systems, okay? But it could be longer. Like in the system I blew up, it was longer. So that was the first insight. The second insight is the settling time is about twice the natural period. So if I upset the loop and I don't break something, but it's like 3 hours later and the loop still hasn't settled out, and that's unacceptable. And if that is less than twice the natural period, you aren't going to fix it with tuning a loop. You got a lag problem, okay? So that was very insightful to me once I realized it. Yeah. And so, yes, that's just the bottom line. So where the model comes into this, that's explaining that concept to students. And I had that problem with a really interesting wrinkle to it on a site over in Berkeley. And so the site was a condenser water system serving a clean room that had an office tower next to it for all the faculty that were doing research in the clean room. And so this is a model of the piping network from the plant to the cooling towers, okay? Now, this isn't a complete model. I haven't drawn in the chillers. There's a lot of stuff missing from this model compared to some of the other ones I'm going to show you. But part of the reason I wanted to show you this is the model doesn't necessarily have to be complete for it to be useful in my experience. All my models are like little in different stages of evolution. Central plant model and the air handling unit model that I'll show you, those are pretty far along. This one, not so much, but I still can use it. And the use here is what we're talking about. This system has, let me see, I got a system diagram someplace. So here's a system. Let me get some of this stuff out of the way. There we go. So this is a system diagram of that plant. Here's the cooling towers. Here's a centrifugal chiller, an absorption chiller, and a modular chiller, okay? Now, physically, if we go back to the model, the centrifugal chiller sits about here, the absorption chiller sits about here, and the modular chiller sits down here, a floor below, okay? This is 14-inch pipe. The flow rate, if just the modular chiller is running, is 200 gallons per minute. The flow rate in a transitional operating mode They never run the centrifugal or the absorber together for a load. They run it to transition. The centrifugal is there for when they don't need the absorber as a heat sink for the cogen plant. So the only time they run the absorber is when they need a heat sink for the cogen plant. In other words, the refrigeration energy is free. So there's a period of time when you're transitioning where all three of those chillers are running. Flow rate then is about 3,400 gallons per minute. These valves right here are the cooling tower bypass valves. So the water leaves the plant and heads to the tower in this pipe, and it comes back from the tower and goes to the chillers and pumps there. There's about 300 feet of pipe each way, which is the point I'm trying to make in a way by showing this model. Given the discussion we just had about lags, do you see a potential problem with how you would go about thinking about controlling this? Yeah, what is it? Anybody?
It's quantity of lag on the condensing water side.
Yeah, and it's a variable lag. So yeah, it's a big lag on the condenser water because at 200 GPM, if you do the math, if you take the volume of the pipe and all that stuff, it's like 15, 20 minutes for the water molecule to get from here over the tower and back at 200 GPM. At 3,400 GPM, it's a minute and a half. So if I did that open loop test with everything running, that apparent dead time would be a minute and a half plus if everything was running. If only the little chiller is running, it'd be 15 minutes before I'd see a reaction, okay, at least. That makes it very challenging to tune the control loop, right? So what I do with the model is I talk to them about lags, I get them to see the problem, and then I say, well, how could you solve that problem? In other words, I guess actually what I'll ask them is, how would you control these cooling towers? And so that gets into a discussion, are the bypass valves and the cooling towers trying to do the same thing or the opposite thing? And I may be assuming some familiarity here. The obvious to me, not obvious to you thing. The reason cooling towers have bypass valves is you can actually get the water too cold for some chillers. A lot of centrifugals will run with colder water than they'll start with. In other words, you can't get them to start because the oil cycle is all contained in the refrigeration circuit, and so the refrigeration pressures affect the oil pressure, and you'll actually trip out on low lube if you have the condenser too cold. Absorbers will solidify if you get the condenser water below about 80 degrees. A centrifugal, you want it below 80 degrees for efficiency. An absorber, the machine will quit working, okay? So sometimes you need a way to keep the condenser water temperature up. And so the bypass valve basically recirculates heat that's been rejected back into the stream going to the chillers to maintain some minimum entering water temperature.
You also have to take consideration your fans too on your cooling towers.
Yeah, and the fans are doing the opposite thing. That's where I'm heading. The fans are trying to get rid of the heat, right? So if you aren't careful, in existing buildings, I'll see a lot of buildings where the valves are recirculating like crazy and the fans are running like crazy. Is that right?
Yep.
Yeah, it's simultaneous heating and cooling, right? It's just a version of simultaneous heating and cooling. So I get them to see that, okay? And then I say, well, how would we control that? How do you think we should control that? Well, but what about the bypass valve?
Free cooling with the bypass and then use your fans afterwards.
Yeah, so the point is you have to sequence them, right? And ultimately, what are we trying to maintain? Are we trying to maintain, assuming a fixed set point, are there multiple places in this system we're trying to maintain a temperature? Or is there one point where we have a temperature we want?
One point.
Yeah, we want the temperature coming back to the chillers to be, the right number, and we want to with that temperature right there in that pipe. Well, if I control off of that temperature, now I have that lag problem, right? And so I get them to see that. And then I say, well, how do you solve that? So how could you solve that problem?
Start by using a temperature sensor on the discharge of your cooling towers.
Yeah.
Because it should be close to the same number.
Yeah, in theory, it should be the same number exactly, just about. There's some losses in the pipe. So you could put a sensor up here to control the tower fans and have the sensor down there control the bypass. Is there any potential problems with that? There's two, basically. What are they?
Failed sensors.
Well, not even failed sensors. Okay, three. Relative accuracy is one. Two sensors meeting an accuracy spec right out of the box could be off, dependent on the accuracy spec, 1 or 2 degrees, right? So the two sensors could think they're making the same temperature and have the tower fans making the water colder than the bypass valve's trying to make it, and so you're simultaneous heating and cooling. You can solve that problem by doing what's called relative calibration. You pick one sensor and say, that's my main sensor, calibrate the other one to it. But there's another problem that can happen. It's similar. Do you have 1 or 2 control loops when you're doing this? You have 2 control loops, so you have 2 set points potentially. So you've got to coordinate the set points. Okay? So I guess, in my let's show you how I use the models, that's what I do with this model. I use it to illustrate lags, and then we talk about the control process, and then I have a spreadsheet tool. Basically, I used to use Icon to try and teach logic, or WinLGC. Those are two. Icon is ALC's programming language. It's a graphic programming language. WinLGC is IDEX ladder diagram programming language for smart relays. And then both those manufacturers make them available for free. So it's another good resource. If you really want to get in and play programming, there's 2 pieces of software. There's a link to them off my website. But the problem I was having was I was ending up spending more time teaching how to use Icon than I was teaching logic. And I realized one day that there were more people familiar with word drawing objects than not. And so I said, I'm going to make myself a tool. And I realized in Excel, I didn't know this, but if you go to the page layout view in Excel, you can actually set row heights and column widths to linear, not like inches, not points. And so if I make the row and column widths the same and turn on snap, I just made graph paper, okay? And so I figured out I could make graph paper in Excel, so I made the graph paper. Then I built a symbol set that's basically FDE's symbol set with some enhancements to make it easier to teach with. And basically put this tool together. And so if you click on the link in the symbol set, oh, PowerPoint's already open. Basically, if that hadn't been open, it would have jumped you to here's the definition of that symbol, okay? So basically, now you can copy and paste symbols. So once we've talked about the control process, I say, well, let's develop the logic for the control process. And so, like, if we were going to do that, we might say, well, I need an analog input. If you say, well, what do we need to make a control process? Well, we need an input, need a set point, we need an output, we need a control process. So we grab all that stuff, and Control C, copy. Where's my blank page? Here's a blank page. And I get all that stuff on the page, and I don't need to do it and spend the time, but the point is we develop the logic. We actually, if we have time, we sit there and make the logic, because that forces them to think through, like your observation. When I said, how do you control them? You said cycle the fans, and well, but there's the bypass valve. It helps them remember that. And then you have to say, well, is the bypass valve normally open or normally closed? Well, how do you figure that out? So you can have a discussion about that. And, well, does that make the control loop direct or reverse acting? You can figure all that out. So by building the logic in this tool, you can basically reinforce the whole concept. And then there's the answer. Like, before the class, if we don't develop an answer, there's a cooling tower that's with 2 speed fans. So, there's one way you could control those towers on that Davis Hall example. Okay, so there's the logic. So they can, see the whole thing, soup to nuts, understand the problem, understand the physics of the problem, understand how you'd solve the problem, and then write the logic to solve the problem. Now, the upside to use an ALC's graphic tool to do that instead of my tool is you could then run a simulation to see if the dominoes are going to fall in the right way. With mine, you have to do it mentally. You have to sort of walk through it just like we did in the olden days when we drew stuff. So anyway, I guess that's sort of, unless there's questions, I'll move to a different battery, I think. I'm gonna get in it.
Do we have the other microphone out there? Yeah. We'll just,
Swap them.
yeah,
Okay.
and I'll go ahead and take care of this.
Okay. Thanks. Whoop. So, make sure I got the stand in the right way. Yeah, does this work? Can you hear me?
Yeah.
Okay. So I guess unless you want to talk about this particular thing some more, I'm going to move to a different model. So if there's questions, that's great. Otherwise, I'm going to show you a different example of something we've been doing with models. Okay. And again, if you want that tool, you can download it off my webpage. There's some examples, the icon and WinLGC you can download off the webpage. There's a couple sample programs for them too that you can play with.
Did you give us the webpage?
Yeah, it's my. If you type David Sellers engineering blog in, that'll take you to my blog. That'll take you here.
Okay.
Here, I'll just I keep saying that. Let's make sure it does it.
Actually, David?
It does.
Okay, and when you get to my blog will look like that. If you click on the picture of the Pittsburgh skyline that my brother took, that takes you to the website. And then if you go to resources, like tools, logic diagram tool, there's an explanation of it and the latest versions of it. And there's also 3 articles, two sets of articles that Jay wrote and one that I wrote, just about control sequences and logic and how to do it. You might find useful, or even something you can use as a resource for a class. And then if you go resources, general resources, PID resources. There's David's book and the link to his website. This is Control Engineering published some really good articles on PID. That's how I found David. It was before the internet. I had just discovered I had a process that I wanted to have a 1-degree proportional band and it had a 10 without going unstable. And I started going through magazines, and Control Engineering had published an article about David and a compilation of articles on PID, and they're really good. There's an interview with John Ziegler in there. It's like really in a nerdy sort of way. It's like Kathy getting an interview of Paul McCartney, right? And so it's an interview with John Ziegler, the guy behind the PID algorithm. And so there's all kinds of cool stuff, and they're really hard to find, so I just put them on my website. And then if you've never seen, this is a Taylor full scope. That's the original PID controller that John Ziegler and David Nichols developed and figured out how to tune at Taylor Instruments. There's the manual for that as well. And this isn't a fill scope, this is a Foxborough controller, similar one. But there's a manual for that, which is just kind of interesting. You can see all the mechanisms. And if you ever hear somebody in process say they want to square the parallelogram, that's a reference to when the controller was properly tuned. There's a mechanism in there that's like a little parallelogram. And when it's tuned properly, the parallelogram is at 90 degrees. That's what a control guy said, we need to square the parallelogram. That's what he was talking about back then. So anyway, that's where you find that stuff. Can you hear me okay? Oh, yeah, okay.
Do you recommend any loop tuners? There's a lot of PID loop tuners out there. There's a lot of processes. Something fundamental and simple enough for students, besides just hooking something up and doing your own PID loop and showing how it reacts differently.
That's what David's software will do. Let me show you. So this is basically David's software. And so right now, I got a loop set up with a 200% proportional band. And let's take the integral time out. I may have just discovered, this is a new laptop. I may have just discovered an issue. Well, let me just run it. Point is, so there's what it looks like with the 200% proportional band. If I got crazy with the proportional band, what if I make that, what do you think would happen if I narrowed the proportional band down to like 10? What would you expect?
Slower actions.
Go unstable, you make it smaller. In other words, the range over which the control signal is going to react is smaller. So the way I think about that, it's like water in a tank, and the pipe's dumping water in, and if you have a float valve and the pivots, actually I have a picture of this, I'm starting to wave my hands around a lot, but if I shove the float up the lever arm to make the water level change that opens the valve smaller, at some point the float's going to end up on the waves. And the wave will be big enough that it shuts the float, but the thing that was making the wave was the water coming out. And so now the float drops. That's instability. So I've made the proportional band too small. So if I do that here, oh, I didn't say enter. I always forget about that. Go unstable. So you can sit here and play with all the tuning parameters and find different responses. David's exercises walk you through. Is that what you were sort of talking about?
Yeah, I'm getting there. I'm messing with lights and stuff like that, just to get a heat sensor and that, but something to see, like how is something reacting? We program a cooling loop into a drive, PID loop, because that's one of the toughest things that I think if we're going to all as educators teach controls is to find something simple enough and fundamental enough that takes that out of it. There's loop tuners and a bunch of others, but as we're all just getting into this now, I think it's really important to have a fundamental but very simple tool demonstrator that we can all understand.
Well, one thing that occurs to me just sitting here talking, I suspect you could make a tank with water and set it up so you could definitely make the splashes big enough to drive it into instability. And
It's just not good to have water by controls.
well, that's true. You have to do that someplace else. Yeah.
We always had rules of thumb for proportional band. When we set up receiver controllers, we would make sure the proportional band was somewhere 15 to 18%, so that we weren't too much or too small.
Yeah, but if you're going for perfection, what you actually do is you keep narrowing that down until you start to see the loop go unstable. And what you just discovered is the safe side of going on. You discovered the safe side of this zigzag. And so then you say, okay, that's where I'm going to stop, and I'm maybe going to go back the other way a little bit. So there's nothing wrong with the rule of thumb thing, but if you're really trying to nail it, that's the process you use. Then if you're doing integral, you actually have to take the proportional band and make it bigger again, so you have room to stick the integral in. And that's what David's book talks about. And I actually have a paper that I wrote, that's how I met him. He peer reviewed my paper for me. So I sort of walk through that process for what it's worth. So.
Are there different theories for PID tuning? For example, I noticed when I work with St. Johnson controls and you're doing PI tuning, and the proportional band may be, let's say, a large number like 100, right? Compared to some other PI tuning or PID tuning where proportional band maximum go is 25 or 30.
Yeah, there's different. The tuning theory is a mathematical relationship that is basically about the lags and the thermal and the responses and the frequencies of the system. What varies from manufacturer to manufacturer is the algorithm they use to calculate the output of the PID loop. There's like at least 2 common algorithms, and I think if you download that PID paper from Control Engineering, that stuff, I think they have an article in there that talks about 4 different PID algorithms. Excuse me. And so since different vendors use different algorithms, the proportional band you'd use on one vendor system is not going to be the right number on another vendor system. But the relationship probably, like if you read Ziegler-Nichols' paper or David's book and discover the tuning rules, like where you find the natural frequency and then you come up with the parameters off the natural frequency, I suspect each vendor's, the relationships between the various parameters would be proportional. In other words, like if you had a proportional band of 200 and an integral gain of 10 on manufacturer A, if manufacturer B's equivalent proportional band was 100, then the integral gain would be 1 or something like that. So the algorithms are different. So are the auto-tune algorithms. I don't have, personally, and we as a company don't have a lot of success with auto-tune. We don't really like it. We think it might be a good way to get in the ballpark on some systems, but to keep it running all the time, we aren't a big fan of that. And my own first initial auto-tune experience was, where was I? Oh yeah, sort of in the interim when we were going from pneumatics to DDC, one of the ways we were getting PI loops on central equipment was we would buy, a bunch of people made them, like Partlow made them, Fuji made them. They called them quarter DIN controllers. It was a electrical size standard, but it was like a box about, I don't know, 4.5 by 4.5, about this deep. It had a controller in it, a PI controller. And so we were using those. And then they came out with an 1/8 DIN one. And I was working with Tom Cox down at SEMO. And he and I both saw them. Like, remember you used to get those bingo cards in the magazines, you just send them in and you get the literature. Now it's all online. But he and I both sent the same bingo card in, and we both got the literature and wrote, we called each other, hey, they got these little tiny 1/8 DIN controllers. We ought to try one. And Tom's like, I'm a heady. I bought a Fuji one and I bought a Partlow one. And I'm going to try them. And so I called him back a couple days later and I said, so how'd that work? And he said, the Partlow one was great. The Fuji one wasn't so great. And Tom was very colorful, so he actually said it more colorfully than that. But basically the message was, he didn't like the Fuji one. And I was down there the next day and we couldn't figure out why that would be. And so we decided, let's swap them. In other words, he had put the Fuji one in one air handler and the Partlow one and a different one, controlling the inlet vanes, I think. And so we swapped them, and they both auto-tuned when we swapped them. So there was something about the dynamics of the one system that the Fuji controller could deal with, but it couldn't deal with in the other system, but the Partlow could deal with both of them. Okay. Another thing you have to watch with auto-tune, at least some of the older ones, one way to do tuning is that open loop test. You basically take the system, put it in manual, get it as stable as you can, and then put a step change in. There are controllers out there that when you hit the auto-tune button would do just that. And that may not be a very good thing with the duct static pressure control process, for instance. I'm going to jack the set point up 3 inches and watch what happens. Well, the duct's going to break for one thing. So you really want to understand how that auto-tune process works before you implement it. So that's just, some of that's personal opinion. But I can tell you there are a number of different algorithms. That's why the parameters are different from manufacturer to manufacturer. So, yeah?
You're talking straight analog control, though most of your rooftop units are stage heating and cooling. But then again, you can use an analog program and then hysteresis blocks and trip points to do the actual outputs.
Yeah.
Have you ever had any experience with tuning anything like that, or have any guidelines for trying to tune like stage heating and cooling on rooftops?
Back in the olden days, one of the advantages to being my age is you got to mess with pneumatics. That's how you learned this stuff. And so back in the olden days, it was not uncommon at all to have all these pressure electric switches on an analog signal. And the pressure electric switches stage the compressors, the duct heat, whatever you're trying to control, tower fans. And so in a way it was a benefit because not only could you mess with the proportional gain of the controller, you could mess with the set points and the differentials on the pressure switches. So I think like the electronic analogy of that, let's let's see. So this is basically a control logic for a modulating bypass valve and a 2-speed tower fan, which is essentially what you're talking about, right? You modulate the valve and then you have to step the fan on and step it off. And so the way this logic works is the output of the loop modulates the valve, and then the output of the loop goes to what amounts to electronic relays, and you can control the set point of the relays to control when the fan stage is on and when the fan stage is off. So not only could you play with the tuning of this loop, you could play with those set points and the spread between the set points to manage how quickly or not things happen. Loop still has to be stable, but you can control how much drift you're going to get between stages and stuff that way. I don't know, does that help?
Except that there's no valve. You're going to just, you'll have your PID in front, and then you have trip points.
Yeah, I'm just saying it would be like this with more outputs, I guess, more digital outputs. So I guess trying to, like the bottom line, basically, you're taking an analog signal and you have to somehow convert that to an on and off, right? And so to me, the benefit of, or the part of the trick was each of the things that's going to make the conversion, which is, in the olden days were pressure electric switches, and now are logic blocks that have an analog input and a 2-position output. You have set points on those that control when it closes and when it opens back up. And by controlling those set points, you can control how quickly things stage up and how quickly they stage down. Like you can put a big gap between low and high speed if you want to. Or you can say, well, I'm going to go 4 degrees and then another 4 degrees. Does that help?
Yeah, that's about what we're doing, but it's a lot of guessing.
Yeah, no, it is. The first step is to get the PI loop stable if you can. I mean, if the loop's unstable, then that's your first problem. You got to get the loop stable. And so for that, start with a big proportional band and narrow it down until you see it starting to hunt, and that's as good as you're going to get. And then put a little proportional band back in. And then add the integral if you want. We hardly ever use derivative. Derivative basically is looking at the rate of change of error. And so if you get it just right, it's helpful if you really need it. But since it's looking at the rate of change of error, and one of the things that can cause the error to change over time is the derivative gain, it can drive itself crazy really easy. It's very hard to apply it. So most of the guys I work with, we just turn it off and decide we need it. And we usually don't use it.
Big P, small I, no D.
Yeah, that's pretty much, although I had one loop that is an oversized valve and I made it an almost all derivative loop. I was just popping the valve every once in a while. And the benefit was it got us out of, basically there's a hospital in Sikeston, Missouri that was coming online the day after New Year's. So think about that. Non-control contractor. We basically suggested to the designer that a line size 6-inch control valve on a steam heat exchanger wasn't properly sized, and suggested a properly sized valve. They rejected our recommendation because we obviously were trying to steal money from them by providing a smaller valve. And so I'm sitting there trying to get this loop to tune like on New Year's Eve and Christmas Eve and crap like that. And I finally got desperate and I tried it and it worked. But the problem, what do you think the problem would be if I have a loop that's going pop, 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 pop? Yeah, you're going to wear this packing out. And I told the operator that, I said, I started to explain it. He said, I'm totally with you. The valve's oversized. We'll buy the right size valve. You got it working. We appreciate it. Go home and see your kid. So I have done an all derivative loop with a little bit of proportional, but it was like not what I'd recommend. So anyway, how are we doing on time? Let's do an economizer example, and then we'll go into the central chilled water plant. Oh wait, that's the wrong folder. So one of the cool things about having a graphic representation of reality is you can do things that you couldn't do in reality. And so this is an actual air handling system. It was in one of Chuck's buildings. You did LeConte, right? LeConte Annex and LeConte when you're at Berkeley?
I'm sorry, David.
Oh, sorry, I caught you off guard. You had LeConte and LeConte Annex at Berkeley, right? Yeah. So this is one of Chuck's buildings that we were working in. And basically, let me get back over to the other side of this model. So it's an old built-up air handling unit. This building was built in the late 40s, right after the war, I think. Like Oppenheimer worked in this building. It's kind of a cool building. And basically, if it took the cover off, so there's something you can do in a model that you can't do out in the field very easily, right? You can take the cover off, and you can see the configuration of the system by looking at it. And so basically, a big old outdoor air damper, a couple smaller return air dampers, which are a clue, filter bank, some sort of funky coil arrangement, a fan, and then a big plenum with the zones coming off of it. And the way that system worked, there were 4 zones, a zone for each floor. It's a 4-story building. And so each floor had a zone with a steam coil on its duct and another zone that had just the air coming out of this plenum, which was basically whatever the economizer was set for. The 4th floor had 2 zones just because physically it had to split and go 2 ways right below. So how it worked is the economizer made 60-degree air, and then out at the zones, if you go look at the drawings on the table, which you can do. Isn't that amazing that we can do that? And you still see there's a resolution problem. But you can read this close enough. At the zone, you had a hot duct and a cold duct with an actuator and a pair of dampers. And basically, as you close the cold damper, you open the hot damper and vice versa. There's no flow regulation. It was just a pure temperature thing. Big old low pressure system. So, built back when they weren't worried about energy, right? And at the time, it was a 100% outdoor air system. But the physics building was mostly offices. There were a couple labs that had some hoods, but it was mostly offices. And so I don't really know this, but the evidence would suggest that during the energy crisis, somebody said, there's got to be a better way to do this than 100% outdoor air. And so they took the relief plan, built a plenum, dropped a couple ducts out of the plenum, cut some holes in the wall, and put return dampers in, and they built an economizer. Okay? So now, just looking at that, if you've been around economizers, there's a pretty obvious clue that this one might not work very well. Does anybody know what that is? Yeah, so you're on the right track. What's the clue you're seeing?
Just the different sizes.
Yeah, that's it exactly. The dampers are way different sizes. So what that means is these dampers are going to have a totally different characteristic curve than these dampers. And if you look at damper characteristic curves, I could show you some, but they aren't linear anyway, unless you size them really tight, and even then they aren't linear. They're kind of linear, okay? So what that means is we assume with an economizer is if I modulate this open 10%, the outdoor airflow is going to increase by 10%. And if I modulate this closed 10% at the same time, the return airflow is going to decrease. If the characteristic curves are nonlinear, that whole relationship goes out the window, right? So just looking at this, would you expect the system to move more air on 100% return air or 100% outdoor air? 100% outdoor air would be what you'd suspect, that's right. The other problem is, if you did the math, let me ask you this, do you guys know the trick for coming up with the ballpark flow rate a unit might be rated for? You have to remember one rule of thumb. You have to remember that designers don't want coil face velocities to be much above 500 feet a minute for a number of reasons, including blowing water off a cooling coil. And in our filters, the filters that we use, the filter guys don't want it over about 500 feet a minute because you'll blow the media out. And if you get special filters for turbines and stuff like that, that's a different thing. So if you remember, 500 feet a minute is the maximum velocity I should see across a filter or a coil. The filters just about always have the filter dimensions on them. Oh, I need to turn something off here. There we go.